This paper presents a method for computing an approximation of ambient occlusion in object space using a custom machine learning regression approach. The ambient occlusion for any given point in a 3D scene can be defined as its exposure to ambient lighting, or in other words, the opposite of shadow cast from all other points in the scene. If done correctly, this is an expensive problem to solve. Essentially, for any given point in the scene, you need to know how occluded it is by all other points. Pre-computed ambient occlusion has existed for quite some time. This can provide a high-quality occlusion term stored in, for example, textures, or per vertex for polygonal objects. However, it's baked and it can't be changed in runtime, and as such does not work well for dynamic objects or dynamic characters. In contrast, a commonly used approach for games is real-time screen space ambient occlusion. There are many different approaches to this, and work continues to improve quality. However, screen space ambient occlusion has a handicap in that it has a lack of information to work with. You can only infer occlusion from what's visible on screen. This means that even for state-of-the-art methods, such as GTAO, assumptions have to be made, and often those assumptions are incorrect. Alternative solutions for dynamic geometry, and characters in particular, are object space solutions. These methods use regression to train parameters using some form of high-quality ambient occlusion as ground truth. This allows for faster and accurate runtime model, and the previous work in this area works well for matching ground truth for poses that are in the training set, and as such, they can be seen as a form of data compression, but they don't generalize well. Our model is a model in this category. Our model is a data-driven approach and includes a fully automated training setup. It's a bi-level object space approach which produces high-quality global effects as well as local detail. It's a skinning-like model which lends itself to fast, simple, and GPU-friendly implementation. It handles poses well that are not in the training set, and its interpretability allows for modes of operation that have not been seen during training, such as character-to-character interaction and ground-to-character interaction. For training, we automatically generate training data by individually rotating each joint to a set number of positions. The ground truth can be generated with whichever method you prefer. We use NVIDIA optics to provide high-quality ray-traced ambient occlusion for training. The way we generate these processes is purely for ease of automation, but any set of poses can be used for the training, such as artist-generated poses can also be used. This is a high-level description of the ambient occlusion model we're using. On a very high level, you can see our model as one that takes the state of the skeleton as input and outputs per vertex ambient occlusion. Essentially, we have a skeleton, and on that skeleton, a number of proxy spheres are placed. We also place what we call key points, which are represented as points with position and a normal. The proxy spheres cast occlusion onto these key points, and each vertex receives occlusion from a number of key points. What we train here are the position and radii of the proxy spheres, the positions and normals of the key points, as well as the weights per vertex for how each key point affects each vertex. Proxy spheres are rigidly skinned, while the key points don't need to be rigid. Looking at the computing diagram for our model, it contains two layers. On top, a dense nonlinear layer, and at the bottom, a sparse linear layer. The input of our model is bone transformations. They drive the transformations of proxy spheres, resulting in changes to their centers. Notice that bone transformations are rigid, so the radii of the spheres do not change. Bone transformations also drive transformations of key points, resulting in changes to their positions, as well as their normals. The nonlinear layer at runtime, we have transformed proxy spheres and transformed key points. Each key point receives contributions from all spheres. These nonlinear dense connections carry global effects but are costly. Therefore, we only use a small number of spheres and key points, typically about 50 spheres and 500 key points per character. The shadow cast on each key point is the sum of shadows cast by all spheres onto that key point. The shadow from any given sphere onto any given key point is the product of the solid angle of that sphere and a front-back visibility function. For a point with a normal, the visibility function, or the visibility ratio, is defined as the ratio of the sphere that's visible inside of the hemisphere of that key point as defined by its normal. Both the solid angle function and the visibility function have closed-form solutions. However, these solutions are not differentiable in the whole range. We want to compute the gradients using these functions during regression training, so these functions are unsuitable for our needs. For that reason, we created two approximate functions that closely match the closed-form solutions, but are differentiable in the full range. A representation of our approximate functions can be seen in red compared to the closed-form solutions. The solid angle projection onto the key points can produce overshadowing when the solid angle of two or more spheres overlap from the point of view of that key point. To alleviate this, we compute the output of the nonlinear layer using a gamma norm function. This works by emphasizing the contribution from the spheres with the largest shadow contribution, or in other words, we sparsify the contribution vector similar to the maximum norm. While this is not an analytically correct solution, it saves us the computationally heavy approach of doing multiple passes to remove double shadowing. Here's an example of our method with the gamma norm function on the right and the incorrect double shadowing on the left. Once we have the ambient occlusion calculated for each key point, in the linear layer, we compute the final per vertex AO as a linear combination of the shadow received by a number of key points. Each vertex only receives a contribution from a few local key points. This sparse linear connection helps reduce computational costs both during training and in runtime. As can be seen in the formula, we include both a weight, alpha, as well as a bias, beta, in order to encode local details at the vertex level. This approach is similar to skinning, so it could be effectively implemented on the GPU in shaders. The objective of our training is to minimize the error for all training poses with regard to a ground truth ambient occlusion. The parameters we modify during fitting are broken down into the layer they're associated with. We perform block coordinate descent to minimize the objective function. For a number of iterations, we alternate between updating the parameters for the nonlinear layer and linear layers separately. For the nonlinear layer, we update the associated parameters using Broyd and Fletcher Goldfarb-Shano method. We choose BFGS because of its quadratic convergence rate and because its requirements for convergence fit our model nicely. For the linear layer, we use constrained least squares to update the weights and biases. The parameters we optimize for each layer are as follows. For the nonlinear layer, we update the rest positions and radii of the spheres, the rest positions and normals of the key points, as well as their skinning weights. For the linear layer, we optimize the weights and biases for the linear combination of key point shadow onto the final vertex ambient occlusion. In addition to the quadratic convergence rate of BFGS, our use of block coordinate descent allows us to perform further optimization of our training process. When performing the update of the relevant layer, block coordinate descent allows us to fix the parameters of the other layer, which means we can pre-compute these parameters. In our case, this pre-computation allows for a speed up of 2 orders of magnitude during training. These first comparisons are related to different types of techniques. On top, you can see the static baked AO to the left and Scree-Spain's ambient occlusion to the right. In this case, it's the Maya viewport screen space ambient occlusion. On the bottom, we can see our method on the left, as well as the ray-traced ambient occlusion ground truth on the right. These are comparisons with other object-based techniques. And in these examples, the runtime poses are the same as the poses in the animations. So this is an example of ambient occlusion compression. And here we see the error visualized in comparison to the ground truth. In these examples, we show how well the method handles generalization. That's to say, the poses are different from the training data. We can see in this case that our model can still closely match the ground truth data, while the previous work starts to struggle. And again, here we can see the error compared to ground truth in the generalized situation. Interpretability allows us to cast occlusion onto the character with high quality from any proxy sphere. So this allows us to, for example, add an occlusion term cast by the ground by attaching a proxy sphere that's always below the ground from the point of view of the character. This is another example of interpretability of our model. We only train our model on individual characters with no knowledge of interaction with other characters or objects. By connecting the proxy spheres of one character to the other, we can allow for ambient occlusion interaction. The system is robust enough to handle this interaction in an agreeable way, even though this interaction is not part of the training set. This is an example of the real-time aspects of our model. We have a scene here with 100 characters, where the nearest characters all cast occlusion onto each other. We see that the characters that are more closely bunched up receive more general occlusion than the ones that are spaced out further. In this example, the linear layer is computed on the GPU, however the nonlinear layer is calculated on the CPU. For most of the frame time is taken up by this CPU calculation of the nonlinear layer. So if this was moved to the GPU, we predict things would be quite a bit faster. And there's no reason why this could not be done on the GPU. In conclusion, we have a data-driven object space ambient occlusion model for animated characters. It's a fast and simple runtime model with no runtime intersection tests. It's robust in that it has good generalization with high quality, and its interpretability allows for approximate shadowing with the ground and interaction with other characters.